Well, welcome to all of you who are here and to all those who are listening on the video. I'm David, the coordinator of the Maths Learning Centre, and while the Maths Learning Centre has the rule of first years first, look how many of you there are. And so that is why I agree to do this sort of thing. Even though personally I never studied differential equations myself as a course, I've learned a good deal about it over the last 7 years in the Maths Learning Centre. And so I can teach you from my perspective of having to figure it out all by myself. And that is quite different from your lecturer's perspective. So people find it helpful. And so that's what I'm offering today. And the first part will be about PDEs. Now, as far as I can tell, in your lecture notes, they're sort of organised by theme of what the PDE is trying to achieve. So he's got like the wave equation and the heat equation and the Sturm-Liouville problem, and they're all just types of PDE, and vibrating strings. They're all just PDEs, and they're organised by what they're trying to achieve. But really, they're all the same methodology as far as I can tell. And so it's not really that useful to organise them by the purpose of the equation, but we really want to organise our thoughts based on what we have to do to achieve the result. And Bessel goes in there, and I'll see if I can figure that out as we go along. Okay, so one of the reasons it's organised by the way it is because to convince you that it's really useful, because it actually solves various useful problems, and to give you some information about how the situation gets to the partial differential equation in the first place. And that's really something that your lecturer in this course, that's their job. My job is to help you figure out the maths bit, and so that's what I'm going to do. And it really works best with an example, and my hope is to just pick one and change it slightly from what's in the lecture notes so it's slightly different, and see if I can point out the pieces that go together in the solution. Right. You are now experiencing just-in-time teaching, which means David makes it up on the spot. So, give me a second. Okay. Okay. I'm going to do this one. Whoa, over there. Okay, so I've got d squared u on dt squared is 25 d squared u on dx squared. Sometimes it's thetas and sometimes it's x and y and t. It doesn't really matter what the letters are. Okay, so that there is a partial differential equation, so called because it's got partial derivatives in it, and there's only a few of them that you're capable of solving. And they have to do with being able to separate the variables. And in principle, it's a similar idea from when you did separable DEs, in that you're actually going to get your function and try and write it as two functions separated, a bit that has the t's and a bit that has the x's. And so that's our first idea that goes behind it. But it's not going to be possible to solve it unless we have some boundary and initial conditions. Okay. Going to do that. and sorry, this is supposed to be a T here, sorry. Damn. Give me a second. Let's do that and hope that it does not turn to crap as we go along. Okay, I'm not actually entirely sure why it's called boundary conditions and initial conditions. They're just conditions. Sorry, did someone? No, it's okay. Please, if I do something stupid, let me know. Well, not everything, because you might be talking continuously, but something really obviously bad. So boundary conditions and initial conditions are just conditions that are going to allow me to create the solution as I go along. I'm pretty sure they're called boundary conditions because they refer to the distance. If x is a distance, the boundaries of my vibrating string are at 0 and pi. That's why it's called boundary conditions, because it's telling me what happens at the boundaries of the x coordinates. And initial conditions, well, that initial means at the beginning, and when time is 0, that's the beginning of time. So that's why they're called initial conditions. But the key is that one of them refers to you sub in a particular value of one of the variables and it comes out to a number, and the other one you sub in a particular value of the variables and it comes out to a function. So you'll notice that these ones come out as numbers and these ones come out as functions. And when they do that, that means that they will appear in different parts of the working. So I'm going to use a different colour for that. Just so that you know it's not part of the working. There are numbers there and there are functions there. And that's important because it changes what we're going to do for our working as we go along. And your functions, in order for this to work, will have the tendency to, really hope I've done this right, will have the tendency to be sines and causes, because what we're going to construct is a Fourier series. So, let's see if I can make this happen. The first step, which is sort of step 0, is to say that u is a function of x. Sorry, I must be near the microphone. And a function of time multiplied together. That's what we're going to assume in order to make this work. And that is where the separation of variables is happening. Okay, we have separated u into a bit that's got x and the bit that's got t. That's the whole idea behind it. And the theory that goes on here is that I want to know what du on dt, d squared u on dt squared is, and what d squared u on dx squared is. And so I'm going to differentiate this with respect to x and t. Cool. I'm going to use dashes for differentiations with respect to x and dots for differentiations with respect to t so that I can keep track of them. So if I do this, du on dt, then this bit with f is just a number because it doesn't involve t, so it counts as a constant. So it'll still be there after I differentiate. And then I'll have to differentiate this, which will give me the derivative of g. And then I'll do it again. So the f of x is still there because it's a constant that's multiplied on. And this is differentiated a second time. And so I get that. And then I can do it with respect to x as well. So du on dx. This time the g of t is a constant and it's multiplied on, so it's still there. And now the f gets differentiated. And it'll happen again. Right. So now we've figured out what d squared u on dt squared was. We've figured out what du squared on dx squared is. And we can sub them back into the original equation. So the original equation was this. And then we figured out that d squared u on dt squared was that, and d squared u on dx squared was this. So that was that's my first step. I'm now up to something that involves these new functions f and g. So instead of trying to figure out what u is directly, I'm going to figure out what these two functions are first. And the next stage is to do what we would normally do when we did separable differential equations, is to put all the t's on one side and all the x's on the other. Okay, and here is our first place where we have to make a decision. That 25 is going to have to go somewhere. It's going to have to go either with the x's or with the t's, and the one that it goes with is the one that has functions. Okay, so you want to move that plane number away from the one whose boundary or initial conditions has numbers in it. That's just going to make our working easier as we go along. That's the reason why we do it. So when we subbed x's in here, we got numbers, and so we're going to make sure that the x's don't have any other numbers. It's going to have just f of x and f dashed x by themselves and no other numbers to interfere with them and leave the g's on the other side. So we're going to do it with the derivatives on the top and the original functions on the bottom. So divide by this. And we'll also divide by the 25, so it ends up over there. So the x is the one that we subbed in to get numbers, and so we left it all by its plain old self, moving all the other numbers away from it. So now the variables are completely separated. I've separated u into two bits, and I've subbed them in, and now once I've subbed them in, I've separated them onto the different sides of the equation. Okay, and I've chosen, just to remind you, x's produce numbers in the conditions. And so I put them by themselves. Okay, so that's the first decision you have to make. Right, now what's the philosophy of this? The philosophy of this is that, well, the left-hand side is a function of t and it doesn't involve any x's at all. And the right-hand side is a function of x and doesn't involve any t's at all. And so really, since those two functions are the same function, we've just said that we have a function that doesn't involve any t's and it doesn't involve any x's, so it must be a constant. So the only way that this could possibly work is if this was equal to a constant. So what we actually have is that is some constant which is equal to the other thing as well. They're both equal to a constant. I know traditionally you put it over this side, but I feel nicer about putting it in the middle because it's equal to both of them. That makes me feel better. Okay, so it must be a constant. The problem is that we don't know what k is. Okay, when we had this second order differential equations right at the beginning of differential equations in this course, you didn't have, the only thing that was unknown was what the function was. Okay, so because you knew you had something's all well defined, all the numbers you knew what they were, and the only thing that was missing was what the function was. But this time we have this k that we also don't know, and that's what's causing us to have to do all this extra work, because we don't know what k is. And we're going to have to run through the different options of what k could be in order to figure out what happens then. So the thing we're going to deal with first is this bit here. That's what we're going to do first. And we're doing it first because it's the easiest one to do first. Because it doesn't involve any numbers other than x, it doesn't involve any numbers other than the unknown k. I've moved that 25 out the way. And also, when I sub in particular values of x, it will produce a number as my answer, as opposed to a function. And so that's going to make my working a little easier. So that's why I'm going to do that first. Whoop. So I'm going to rearrange that. So we've got... Okay. So I get this. And I'm going to rearrange that. I'm going to times by the f, get it up there, and bring the k over. So that will allow, I can rearrange this into that if I do 2 steps of algebra. And I've removed the x's because they're just getting in the way now. The reason I did that is because now this is great because it's a second order differential equation, second order homogeneous differential equation with a constant coefficient. We don't happen to know what k is, but it's still a constant. And so that goes all the way back to Maths 1b. We did them in Maths 1b. And so we're going to go, cool. I'll have to deal with the boundary conditions in a minute, but I'll get to them. I should do them now, actually, because it's traditional that your lecturer will do them at the beginning, because what they're going to do is often in an exam, they'll do this bit for you. Okay, they will tell you what the answer is to this bit, so you don't have to do it yourself. And it happened in the Maple TA at least once as well. So I need to make it look like what it will look like in those situations, so it's easier for me when I see it later to know what's going on. So let's deal with those initial boundary conditions over here. So the boundary condition said that when x was 0, regardless of what t was, u came out to be 0. So let's just see what that means. So let's see. I need a title for this section so I don't get lost. Let's call it the second step. Okay, so let's see. We know that u of 0t is equal to 0, but that's the same as saying that f of 0 g of t is equal to 0, which means that f of 0 is 0. Okay, so I've gone back to my boundary conditions. Gone back to my boundary conditions, and I've subbed in, I've just done exactly what I've said, but u is really f of x, g of t, so I've subbed in the 0 for x and the t for g, and then I've divided by the g of t. And that's pulled a slight swifty there, but the point is that regardless of the value of t, g of f of 0 always comes out to 0 no matter what t is. So if I just pick a value of t such that it isn't 0, I'm allowed to divide by it. So that's okay. So I'm allowed to just ignore the normal thing where I have to say that this is not 0 in order to be able to divide by it. So f of 0 has to be 0. But the other boundary condition was that pi t is also 0. So that means that f of pi g of t is 0. And again, I'll divide by the g of t and I'll get f of pi equals 0. So what you might notice is this process is really only going to work if these two come out to 0. It's not so much that they're numbers, it's the fact that they're 0 that's actually the useful bit. Because if it wasn't 0, when I divided by the g of t, I'd get like 1 over g of t or something. The point is that when I go 0 divided by g of t, the answer is still 0. Okay, so now I have this. So now I need to solve this. F double dash minus k, k of f equals 0, with f of 0 equals 0 and f of pi equals 0. I do need to point out sometimes your boundary conditions will refer to the derivative of u, and so you just need to pay very close attention, because you might have to differentiate u first. Do like u dashed or u dot before you can do that. That happened in one of the Maple TAs that someone had yesterday, that they forgot to notice that there were dashes involved. They subbed it all into the original function and it just didn't work. So really pay attention to when there's derivatives being mentioned. Okay, so we're here. So to point out that sometimes when you get to this stage, it's actually f dashed, or something like that. So please pay careful attention to that. So now we have to solve this. And this is a second order differential equation with constant coefficients and some conditions, and we can solve that using the methods that we used back in Maths 1B. So let's see if we can figure that out. What we would normally do is you do the characteristic equation. Okay, so the second derivative becomes lambda squared. The first derivative, which isn't even in this equation, becomes lambda, and the original function just disappears entirely, and we end up with this, and so we get lambda squared equals k. Note that sometimes the way that your original equation is set up will have a plus k in that spot, and that's all right, as opposed to okay, too many k's. That's all right to have a plus k there, but it will change ever so slightly what your working looks like, because it'll be an extra minus, so you have to deal with that. If you get to choose yourself, it does work quite well for k to have a minus next to it. Okay, so what's going to happen is I'm going to need to consider what happens when I do when I figure out what lambda is. Like lambda is going to be plus or minus root k. Okay, I'm going to write this in, but most people don't put it in. So there are three situations in second order constant coefficient differential equations, and they correspond to whether the lambdas are the same, whether the two solutions for lambda are real, and whether the two solutions for lambda are complex conjugates. And depending on what k is, we're going to get different answers. So if k was 0, we just get lambda equals plus or minus 0. So we just get two of the same answer. If k was positive, we'll get lambda is plus or minus root k. That's two real answers. And if k was negative, well, we're going to get an I when we do the square root. So depending on the value of k, we're going to get different answers. And so we have to consider all three of them separately. Technically. It's actually true that pretty much just one of them is going to be the one that works. But we have to consider them all. So here we go. So k equals 0 will mean that lambda is actually just two zeros. It's plus root 0 and minus root 0, which is just two zeros. Okay, so I've got a repeated root. So if you want to go back to the way you did it back in Maths 1B, you can say, well, that would mean that f would have to be a e to the 0x plus bx e to the 0x, because that's what you would do with a repeated root. Not technically necessary to do that, but it does match with what with the story I'm trying to tell here. Okay, so that's what you do when you get a repeated root. But of course, e to the 0 is just 1, and so this is really just the same as a plus bx. So e to the 0x is just 1, e to the 0x is just 1, so we get this. The other way of dealing with that is to go, well, if I went all the way back to here and put k equals 0, that would mean that f double dashed is 0. So when I integrate it once, I get an a. When I get a b. When I integrate it another time, I get a bx plus a. So I could do that if I wanted. This way allows me to not have to backtrack and do a different bit of the working. But I could have done that, and I will put that in a different colour if I wanted, or k equals 0 means that what we actually have is f double dashed equals 0, so f dashed is a constant, because when we integrate once we get a constant, and therefore f will be bx plus another constant. So that's the other way of doing the same working. You can do whichever one you like. It's good to know that they're both there. Okay, so that's what the solution will look like if k equals 0. And what we need to do is we now need to figure out whether any of those solutions aren't 0. Because we already know that 0 is a solution. So when we come back to here, if f was just the 0 function, like f equals 0 no matter what x is, then 0 minus k times 0 is totally 0 every time. So I don't care because I knew that already. So I need to make sure that I get answers other than just f equals 0. And so I need to find out what they are here. So now I'm going to use my, my boundary conditions. So I'm going to use my conditions. So I know that f of 0 is supposed to be 0 and f of pi is supposed to be 0. So when I sub in 0 into this one, I get f of 0 is a plus b times 0, which is a, which is supposed to come out to the answer of 0. So a is 0. Awesome. So actually f is just bx. All right. So now let's sub in this one. F of pi is b times pi, which is supposed to come out to the answer 0. So if I divide by pi, I get b equals 0. So actually, f is just 0 plus 0x, because that's what a and b are. Awesome. So f is actually just the 0 function. And what most mathematicians will do is they'll write a triple equal sign to say it's exactly equal to 0 all the time. It's precisely 0, not just equal to 0. Not just equal to 0 now for this particular value of x, it's equal to 0 no matter what x is. So there's f is exactly 0. So that didn't help. Damn, we knew that f was 0 was a solution already, so we're going to have to actually try something else. So let's try the next one. What if k is positive? So this is my second situation, k is positive, in which case my lambda is going to be plus or minus root k, which is two real solutions. In order so that we don't have root signs flying everywhere, we are going to declare that k is already something else squared so that my working looks nicer. So k is, I believe it's traditional to do with mu. No reason that I can see to use a mu, but there you go. Okay, so if it's something squared and that mu is a real number, it'll totally be positive. And that will mean that when I do the square root, it'll come out to be a plus or minus mu. So that means my lambda squared is mu squared, and so my lambda is actually plus or minus mu. So I've got two solutions for lambda, two real solutions for lambda, and so therefore f is going to be a e to the first real solution x plus b e to the second real solution x. Okay, and that's from our knowledge from the past. That's where all our hub central chairs are. All right, bring them back later. So that's my solution this time. And now I'm going to use my conditions again. F of 0 is supposed to be 0, so let's see. F of 0 is a e to the mu times 0 plus b e to the minus mu times 0. And e to the 0 is 1, so we just get a plus b. And this is supposed to come out to 0, because f of 0 is 0. Awesome, a plus b is 0. Damn, it's not telling me anything useful yet. But I might just do this. B is the same as minus a. And I'll sub it back in. So therefore f of x is actually a e to the minus mu x minus a e to the minus mu. So, damn, a e to the plus mu x. Okay, so what I've done is I've subbed in b equals minus a back into the original just to make my life easier. The reason you might do this is if you actually had to differentiate the f to get the other condition, this would be easier from this point on. So now let's see, f of pi is supposed to be 0 as well. So we get f of pi is a e to the minus mu pi minus a e to the crap plus mu pi. Did it again. Minus mu pi. Too many minuses. Awesome. And that's supposed to be 0. I don't like it. But what I am going to do is this. They do both have an a. So pull out the a and note that that has to be equal to 0. So here we go. A times some crazy number is 0. And this number is not 0. The reason I know this number is not 0 is because mu isn't 0. The only possible way that e to the mu, e to the plus something can be equal to e to the minus something is if the something is 0. Okay, because this would be, because mu is positive, this is like something bigger than e, and this is something smaller than e, so when you subtract them you won't get 0. So what we have here is that this is not 0, so therefore we can divide by it and get a equals 0. Awesome. But if a is 0, b is minus a. So b is, no, not enough room. Next page. So b is minus a, which is 0 as well. So f is in fact equal to 0 e to the mu x minus 0 e to the minus mu x, which is, so f is 0 all the time, no matter what x is. Curses! We still haven't found any solutions. This is the way it's supposed to go. If you're very lucky, you're supposed to find the one that comes out to 0, both of them first. The key is, if you choose to do the positive one first, it's probably the one to go with. And the reason I know that is because, well, normally you want sines and causes to come into here because you're looking for Fourier series. And so that's the one with the I is going to be the one that produces the sines and the causes. Now that's probably not true in general for actually solving actual differential equations, but for doing exams on differential equations, it's really good advice. Sorry? No, because you're supposed to definitely confirm that the other ones don't produce answers. It's all part of the working. You have to show that. Pretty sure. This is one of the reasons that they often do this part of the working for you. They just tell you what the answer is. I cannot guarantee what your lecturer is actually looking for. It's the sort of thing that you should ask on a discussion board and say, so, do you want us to do all of it? Yes?
In regards to that, like sometimes when we get initial conditions given to us that are like cosine or sine, then we already know that we need a cosine or sine. Can we say that as an argument, or do we have to actually go ahead?
Okay, so for the recording, the question is if your initial conditions, for example, have a cos in them, going, yes, that means we'd be expecting to get a cos in our answer. Is that a good enough argument to just go there first? No. Because you have to properly confirm it doesn't work in the others. Yes?
If there was a negative sign in front of the 25 and the initial problem,
yep.
Then would the case where k equals mu squared greater than 0 be the cos sine one, and the k equals negative mu squared be the e to the power of something x?
So I'm going to answer a different question than you asked and then answer your question. So if this was a plus here, then yes, k being negative would correspond to the one I just did, and k being positive would correspond to the one with the complex solutions. So do whichever of them gives you the complex solutions for lambda at the end. But your question was, if this was a minus 25 here, well, that's completely irrelevant because you're going to move that number away and put minus the 25 over here anyway. So it's not the original one, it's what you end up with after you've done that process. So if you get the chance to set this all up yourself, you can always arrange for it to be a minus k, because you get to set it up. Because you can put the constants wherever you want. You can just move them away so that you get a minus k. But it has been known in things like Maple IIA for them to just start, not to start with a PDE, but to just randomly start with something like randomly start with this, but with a plus sign. So if they didn't give you the PDE and just went straight to this, and they had a plus sign, you'd have no choice but to run with what they gave you. Is that all right? Does that answer the question? Cool. So we are now up to the final bit. And now I've lost my pencil. There it is. We are now up to the final bit, and now we've had lambda is 0, we've had lambda is positive, and now, not lambda, k. K is 0, k is positive, and so now k is negative. Okay, so k being negative, I'm still going to have to square root it, right? So it would be great to call it something squared so that I can square root it. So I'm going to say let k be minus, I don't know why p. If I was doing this, I would use the Greek letter nu, because it's after mu. But nus look like v's, and no one can write them anyway. And so p sounds like a reasonable one, because is it L, M for mu, N for nu, O is just 0, so P would be the next letter. That makes sense. Cool. I've got a good reason for using a P now. So why don't they just use M for... Anyway. Notation's crap. So conceivably you should be able to use whatever letter you want, but it's good to use the one that your lecturer uses, because then it will match what the solutions look like, and the marker will not have to work so hard to mark your solution, and happy markers are generous markers. So k is minus p squared, which means that lambda squared is minus p squared, which means that lambda will be plus or minus pi. So the p squared gets rooted to be a p, and the minus 1 gets square rooted to be an I. Cool. So back in Maths 1b, it went like this. Alpha plus or minus beta I got you an e to the alpha x cos beta x, and an e to the alpha x sine beta x. Like that. And so we've got that, but my alpha is 0. So I'm going to write it explicitly. You can skip the explicit bit if you want, but I feel more comfortable this way. So my f is going to be a e to the 0x cos px plus b e to the 0x sine px. But of course, e to the 0x is just 1, so you don't have to put that step in if you feel comfortable not doing that, but I have a certain pattern of behaviour that I need to follow, or I'm not going to get to the end. Okay, and here's where my cos and sines come from. Personally, I like to put the a with the cos, because then both the a and the b and the cos and the sine are in alphabetical order, but that's just my little quirk. And I do like to have them in alphabetical order for various other reasons. So that's what we've got now, and now we're going to use our conditions. So we know that f of 0 is supposed to be 0. So let's see, f of 0 is a cos 0x plus b. And sine of 0 is 0, and cos of 0 is 1, so I get a. And that comes out to 0, so a is 0. Sweet. So that means that therefore f of x is actually a, no, there is no a, because a is 0. B sine px. Okay, that's where we're up to now. We haven't used our second condition yet, so let's put that in. Also, f of pi is 0. Yep, that's all good. F of pi is 0, so let's see, f of pi is b sine pi x. Yes, pi p, thank you. It makes me happy that people are confident enough when I'm teaching you to just call stuff out like that. And actually to ask questions. So that gives me a great sense of pleasure that people are confident enough to ask questions of me. It means that my whole 7 years of answering people's questions has not been in vain. So there we are, b sine p, and this is supposed to be 0. Okay, so back in the other ones, at this stage I was able to say, oh well, that meant that b had to be 0, and therefore the solution was just identically equal to 0. But b doesn't have to be 0 for this to come out to be 0. Because what if p was precisely the right number to make sine of pi p come out to 0? So just for my own purposes, I like to say b is not necessarily equal to 0. Just for my own purposes, just to remind myself that this is why I'm getting to my exact answer, and it's not necessarily equal to 0 because sine of pi p could be 0. So it could be that sine of pi p is 0, and that means that the b doesn't have to be 0. And sine of pi p being 0 means that the thing inside it has to be an angle that makes sine 0. So let's see, sine is 0 here and here, because it's the y coordinate. Okay, so that means that pi p would have to be an integer multiple of pi. Now p is a positive number. I actually should have told you that at the beginning when I said that, you know, k is p minus p squared. No particular reason. We can choose it to be positive and it'll be fine. So p is a positive number, and so it's actually a positive integer multiple of pi. You'll note that sometimes if you have a cos, I'll write this down in a second, if you have a cos, sometimes it'll be an odd multiple of pi on 2 or something like that. So I will put that down when I get to the end. If I forget, remind me. Sometimes at this stage you have to say it's an odd multiple of pi on 2 or something like that. Okay, so it's an integer multiple of pi, so we have that pi p is in fact equal to some multiple of pi for n equals 0, 1, and so on. Note very carefully the range of n's that you're supposed to use if they tell you in advance. Because sometimes they tell you that you're not supposed to use n equals 0, in which case you have to change the way that you arrange it, because you'd have to have like n minus 1, so that the 0 is still in there when you put n equals 1. Okay, and so therefore p is just n. Sweet. Okay, note that if I had instead back there had said that f of 2 pi was 0, I would have gotten a 2 pi p here, and I would have gotten n on 2. If I had said that maybe pi on 2 was 0, I would have gotten pi on 2p, and I would have gotten p is 2n. So depending on what goes here, changes what expression involving n ends up here. So be careful, it doesn't always come out to n, and the reason it comes out to something different is because of your numbers. Okay, so p is n. Yes?
N can't be 0, because you just,
You're right, n can't be 0. Thank you. Good move. In fact, that's an extremely important point. So n can't be 0 because p isn't 0, because k isn't 0. That's what you're saying?
Yes.
So when I come back here, k is properly positive, because I've already covered k as 0. Oh, sorry, negative. Damn, my pages are now mixed up. Should have numbered them as I went, really. K equals 0. I've lost a page. It's underneath. No. Oh. That distresses me greatly. Right there. It's right there. K is negative. For p not 0. Cool. So since p isn't 0, thank you very much. Since p is not 0, n here can't be 0 because that would make p 0. Awesome. Thank you very much. Whew. Disaster averted. And so now p is n, so my k is actually minus p squared, which is minus n squared. This is where the lambdas come in. So you know when they say lambda n, that's what this number is. So this is now an eigenvalue. The reason it's an eigenvalue is because back here, way back here, f double dashed is equal to kf. So that's telling me that when I perform the action of double differentiation on f, I get a multiple of f. Same as back in Maths IIA, if I perform the action of multiplying by a matrix, I get on v, I get a multiple of v. So this is comparing to AV is lambda v. That's why it's called an eigenvalue, because I did an action on the function f and I produced a multiple of f. The same as if I did an action on the vector v and I produced a multiple of v. That's why it's called an eigenvector, eigenvalue. And an eigenfunction, because it's an eigenvector, but it's not really a vector, it's a function. So that's why it's called an eigenvalue. And so we're going to say the eigenvalues are lambda n. Right. And the eigenfunctions, well, they're the functions when I sub in what p is into my function. So my eigenfunctions look back here. F is b sine pi p. That is my solution. No, back. One more step. F is b sine pi x. Px. B sine px. That's what f of x is, based on the solution, what the information I have so far. Because I couldn't figure out what b was. Okay? And I know what p is now. It's n. And so they're my functions that go with the value of p. So they are my eigenfunctions. It's just, these would be f's. Yep. So f was equal to, I'll actually just change that ever so slightly. F was b sine px back in the previous page, which means that my eigenfunction is just the sine px. I don't need the b for the same reason as when I found eigenvalues back in Maths IIA. When you find eigenvectors, when you find eigenvectors, it's t times a vector and you ignore the t. Same deal. It's b times a function and you ignore the b. Okay, because any multiple of that will do, because you're just going to do multiples of them anyway eventually. Yep.
With that eigenvalues lambda n, is it lambda n equals k or something like that, or is it just lambda n equals k?
That's interesting. I should go back to that. Just a second. You're right. No, the k is the lambda. This is why this is all confusing, because we're using lambda to mean two different things. This lambda here, is the one that belongs with the characteristic function. This lambda here is the one that belongs with your eigenstatement, which is the f double dashed is equal to kf. Yes. So be careful. The lambda back here that said that it was equal to lambda squared is a different lambda. This lambda here lambda squared there. That's a different lambda from this lambda. This lambda is just k. Yes. I'm sure there's a really good notational way of not being confusing, but since I'm making it up on the spot, I can't go back and change it now. I'm very sorry. Maybe next year, but it's too late for you by then. Well, no. It will not be too late for you by then because you'll all pass. Okay. Really, I really hope, you've got a couple of weeks, so, you'll study and you'll pass. And it'll be all my fault because I did this revision seminar, right? Okay, so that's where we are. Now here's the thing, that's only step 2. All right, so look at those several pages of working that I did. That's step 2. That's my second step. And it took me what? I don't know, 5 pages. My writing's pretty big, but still. In lots of assignment questions and exam questions, they do that bit for you. So do not launch into that in an exam before you check if they happen to have told you how to solve this equation. They might put a lambda in this spot, but they might say, well, consider the differential equation x double dash minus lambda x equals 0 with these conditions. Well, that has these solutions. What that's doing is all of this working for you and skipping straight to the end. So don't do all that work because it's a waste of time if they've already done it for you. And that's a general message for all maths, right? If they've done part, notice if they've done a bit of it for you. Okay, so my third step is to figure out what's going on with the other function. Okay, we've dealt with the f. We're going to go back and deal with the g. Sharpen my pencil. Whoa. So I'll go back to my original equation. Here I am here. I've dealt with this bit that involved the f. Now I'll deal with the g. Or well, if you like, it might not be called g, it might be called something else. But you'll deal with the other variable. So I have that 1 over 25 g double dot t over gt equals k. But the point is that k, we just figured out what k was. K is minus n squared. That was way back because my original one had a 25 here. And so when I went back to my first page, when I rearranged the differential equation that had a 25 in this spot, I ended up with a 1 over 25 over here. Is that okay? I didn't hear where that was, so I can't look in the right direction. Okay, and you'll notice in your notes, there's a 1 over c squared here if I zoom that in, but I don't want to mess up my thing. There's a 1 over c squared just... Yeah, you can totally see that. There! We can now see it, just there. That's my 25, the 1 over the c squared. It's minus n squared. Okay. I may have to change the original question, I'm sorry, but just we'll see how it turns out. Okay, so now I need to solve this differential equation. So I'll ignore the t's and I'll just do it with the double dots. So like that, times both sides by 25, times both sides by g, and I'm now here. And now it's a second order differential equation with constant coefficients. Yeah, totally could. Thank you. And so now it's a second order differential equation with constant coefficients. So I will do a characteristic equation. If you think about it, I really could have skipped both of those steps and just done the characteristic equation directly from here. I could have gone straight to lambda squared equals minus 25n squared, because it always comes out that way. So shifting it from one side to the other and back again is probably just introducing more chances to lose minus signs. So it's probably okay to just go straight from there to there, if you want. And so lambda is equal to 5n plus or minus 5ni. Now here is something really important. Here's something very important. In my situation, n was not allowed to be 0. It had to be 1, 2, 3, etc. Because I had explicitly ruled out the fact that p was 0. But if n is equal to 0, well, something interesting happens, and I'll talk about that in a moment. How long have we been going for? Okay. Okay, so if n was 0, same as back before when k was 0, I'll get a different answer than I would if n isn't 0. Because this would not actually be true. I wouldn't get an I if n was 0, I'd just get 0. So, just important to note. And so therefore I'm going to get that G is a x t t. Like that. Which is of course this. Note that the coefficient that goes with this value of n, maybe if n is 1, it'll have its own coefficient. If n is 2, it will have its own coefficient. So what we actually want to do is we want to label our coefficients to match the n's that I'm currently using. So now I know what G is. Sweet. Okay. We're nearly there. I may have to change my original question as I stated earlier, so please bear with me. Okay, so what have we done so far? Let's see. We've dealt with the f, and that's told us what the k is and what the eigenfunctions that go with that are. We've dealt with the g now, and now we have functions that go with f, and in fact I'm going to call this gn, even better. We have a whole lot of functions gn and a whole lot of functions fn, and we are going to combine them to make un. Now what was fn? Thank you. Nope. I'll deal with that in a minute. Actually, you're right. Nope, I don't need that. Because I'm going to times it by this, as this has already got constants. So the question for the listeners and for everyone else who didn't hear, do I need a bn here or something? No, I don't, because there's already one here. And I'm going to multiply them together anyway, so it's all okay. I don't need them. So now I have that un and there we are. Awesome. And so therefore u is the sum of all of those things from 1 to, well, infinity, I suppose, because they're all the options for what n could have been. Okay. Awesome. Got a solution. Great. Okay. So, right, this is my general solution. Okay, it's got A's and B's. I don't need a constant next to the sign because there's already two constants here, so I don't have to worry about that. I now have to figure out what the A's and B's are. All of them, all infinitely many of each of them, yes?
I might have missed this before, but how come the second time we don't have to go through the different cases?
How come the second time we don't have to go through the different cases? For the k, because we already figured out that k had to be minus n squared. Yeah.
Sorry, explain again how come the series only gets to start at n equals 1, and then what will be the case when the series gets to start at n equals 1?
Back here, if I end up with a sine, it'll always start at 1. But if that was a cos here, if I had, say, cos pi p, then pi p will have to be an odd multiple of pi, which would be like n equals 1, 3, 5, and so on. But what you actually do is you go, well, 2n plus 1 to create your odd numbers, and then n is 0 and 1 and 2 to make the numbers 1, 2, 1, 3, and 5. I will write that down properly in a second. Okay, so now we're going to have to use our conditions. So we already used the boundary conditions. We used them to figure out what n was, what that k was, the minus n squared. Now we're going to use our initial conditions. So u of x0 is supposed to be cos of 2x according to the initial conditions. So what that means is that when I sub in x equals x and t equals 0 into that formula there, I will get cos 2x. And therefore I should have actually made them all sines. Sorry. Sorry guys. Sorry. No, that's not going to work. The reason I know this is that when I sub t equals 0 into this, I'm going to get a sine. So, yeah. Wouldn't it be nice if you could just change the question in the exam? Well, you'd like to hope that your lecturer has done it properly. I'm very sure, based on all the working that I did, that it really is a sine. Yes. Okay. So this is actually a sine. Oh, and I should point out to you, the reason I know that there's not a constant there is because a constant is an even function and cos is even. And so the constants go with the causes, whereas sine is an odd function. There can't possibly be a constant if they're all made of sines. So if you do a Fourier sine series, it won't have a constant term. A Fourier cos series will usually have a constant term. Okay, sine 2x. So when I sub this in, u of x0 is so we get an cos of 0 plus bn sine of 0, which is totally an cos of 0 is 1, b sine of 0 is 0, this is an sine nx. So here's the thing. This is supposed to be equal to sine 2x. So it's supposed to be a combination of sine x, sine 2x, sine 3x, sine 4x, sine 5x. it's supposed to be, let me just put an extra bit of working in there. This is A1 sine 1x and A2 sine 2x and A3 sine 3x, etc. And this is actually just equal to sine 2x. So, A1 has to be 0 because it doesn't line up. A2 has to be 1 because that's what lines up. And A3 has to be 0, and A4 has to be 0, and A5 has to be 0, and all the other ones have to be 0. So the only matching sign is this one. All the other A's have to be 0. So I've got that A1 equals 0, A2 equals 1, A3 equals 0, and all the rest of them equals 0 for the rest. Because that's what lines up with my sign here. Okay. The other initial condition was that u sub t, x0, is 3 sine 4x. So let's see. I'm going to go back to my original expression for u, and I'm going to have to differentiate it with respect to t. I'm going to need a bit more space. All right, well, the sign nx doesn't involve a t, and it's multiplied on, so it will still be there after I differentiate, because constants multiplied are still there after you differentiate. And then the an cos 5nt, well, the cos will differentiate, the an will still be there. The cos will differentiate to give a minus sign. And I'll have to multiply by the derivative of that, which is 5n. So that's the derivative of that bit. And the bn will still be there, and the sine will differentiate to be a cos, and the 5n, because I have to times by the derivative of that, because the chain rule, it will come out. And so that's my derivative of u with respect to t. And so then ut of x0 will be what I get when I put t equals 0 into that. So when t is 0, this is 0, but just for completeness' sake, so that's 0 there, 5nbn sine nx. Okay, so I'm going to do what I did last time and write that out. When n is 1, I get 5 times 1 b1 sine 1x. And when n is 2, I get 5 times 2 b2 sine 2x. And when n is 3, I get 5 times 3 b3 sine 3x. And when n is 4, I get 5 times 4 b4 sine 4x, and so on. And this is all supposed to be equal to 3 sine 4x. So, is that right? That's from back here. This is a 4x here, sorry. I like to claim that my handwriting is why I'm so good at teaching medical students. So, I don't have a sine x, so b1 must be 0. I don't have a sine 2x, so b2 must be 0. I don't have a sine 3x, so b3 must be 0. I do have a sine 4x, so 5 times 4 times b4 must be 3. So I've got that b1 is 0, b2 is 0, b3 is 0, and 5 times 4 times B4 must be 3, which means that B4 is 3 on 20. And then all the rest of them are 0 as well. So let's see what I've got lined up here. I've got I lost a page again. I have that A1 and A2, no, A1 was 0, A2 wasn't, and all the rest of them were 0. Damn. So, A1 was 0, A2 was, what was A2? 1? A3 was 0, and B1 was 0, and B2 was 0, and B3 was 0, and B4 was 3 on 20, and all the rest of them are 0. So that means that the only ones that actually appear in my actual function are these ones. So therefore U is actually, just trying to find my original U. Put it underneath. So this is my formula for U here. U is only occurs when n is 3 and n is 4. They're the only times that anything actually happens here. Well, n is 2 and n is 4. Only ones that actually anything happens. So n equals 2. We get sine 2x A2, which is 1. No, I'll just put them all in. Cos 5 times 2, which is 10t. So that's what happens when n is 2. And when n equals 4, I get sine 4x A4 cos 5 times 4, which is 20. Sine and 5 times 4, which is 20. I get that. And now I can sub in the values of A2. Sorry, that's not an n. Damn, that's a 2. I'm specifically using n equals 2 all the way along and n equals 4 all the way in this. And the reason I've chosen those ones is that these are the only ones that actually have any non-zero values. And then just to be sure, I can sub in the actual values of A. A2 is 1, but B2 is 0. So it doesn't really exist. And A4 is 0, and B4 is 3 on 20. And that is my solution. Just to make it look prettier. There you go. Simple. Okay, so I did have a couple of comments of a what would happen if variety. What would happen if? So if we were doing this and at some point we ended up with what would happen if we got to here? So what would happen if Okay, what would happen if we got to there instead of where we actually got to, which had a sign? What would happen if it was a cos instead of a sine? That's what I'm asking. Well, then we would have gone, well, b is not necessarily equal to 0, since it could be that cos of pi p equals 0. And then we go, just a second, cos is 0 here. So that means that pi p is an odd integer multiple of pi on 2. Because we've got 1 pi on 2 and 3 pi on 2 and 5 pi on 2 and 6 and 7 pi on 2. So we would say, so pi p is an odd number times pi on 2. 2n plus 1 is an odd number. Guaranteed to be an odd number no matter what n is. And in this case, n would have started at 0, okay? Because I would have, when I put n equals 0 into this, I get 1 pi on 2. And so that's the first positive odd integer multiple of pi on 2. Yes?
So if n equals, like if you're given a question where n has to be starting at 1, would you do 2n minus 1?
Yes, and I will write that down. So what if what if it had to be n equals 1, 2, 3, etc.? Well, in that case, 2n plus 1 wouldn't work, because when I put 1 into it, the first multiple would be 3 pi on 2, and I've missed one. I've missed this one, the first one. So I should do 2n minus 1, so that when I put 1 into it, I still get a plain pi on 2. Really, really important. Okay? Yep. Yeah, if you miss the first pi on 2, it might not be the end of the world, because it may possibly work out. So in our solution before, only n equals 2 and n equals 4 actually gave us solutions. And so it may be okay. It might coincidentally be okay. But it may be that that very first solution is the one that you need. And so therefore you'll miss out on it. Does that answer the question? There was another what if that I was supposed to do. Does anyone remember what it was? Oh, yes. Sorry? Yeah, it was to do with the constant. So what if n was allowed to be 0? Okay? What if I got to here I don't know, what was it again? You know, what if I got to here? I don't know. Well, it wouldn't be a 3, it'd be a square number, wouldn't it? Just making one up for you. So what if I got to k equals that for n equals 0, 1, 2, etc.? Okay? What if I was allowed to have n equals 0 in that situation there? Okay? Right. Then I would get to my so suppose this is where I was. Okay, this is just a big suppose this was the question. Okay, what if we got to there? Okay? Then when I did all my rearranging, would get to that. And I'd be able to do my characteristic equation. So lambda squared equals minus 25n squared on 9. I'd get to there. And here's the problem. I would get a different answer depending on whether n was 0 or not 0. And I would need to consider them separately. So if n is 0, I get lambda squared equals 0, which means that lambda is a double root, and I'd get g equals I'd get that. And that would be a plus bx. But if n wasn't 0, all the rest of them, I get lambda squared is, and I'd get complex solutions. I'd get that with an I, because that would be complex. And I would get g equals eventually a cos 5n on 3. Oh, these are supposed to be t's. Sorry. T. Okay, so this would be the solution for Gn, but G0 would be A0 plus B0t. So I'm going to get a different solution for the first one. And so I'm going to get, so I might get, you know, suppose Fn was like sine, oh crap. Sine n on 3x. Then I'd get that my u, so for n equals 0 there's a different answer. So for n equals 0 I'm going to get a0 plus b0t. Oh crap. I'll do this as a cos if you don't mind. I'll get a0 plus b0t cos 0 x. So that's my g and that's my f. And for all the rest of them, I'll get an cos 5n on 3t plus bn sine 5n on 3t times cos n on 3x. Okay, so the important thing is that there will be this extra term. And so what will happen is if you sub in a value of t, you are going to get different answers, and you might have a constant term out the front. Okay, that's all the what ifs I can think of at this time. Do be aware that that's my other what if. I won't go through the whole thing, but what if the boundary conditions were something like that? Ux 0t equals 0. And then what that would end up meaning is that later you'll get like, that means that, so u is f of x, g of t, so ux will be f dashed x, g of t. So ux of 0t will be f dashed of 0, g of t, which is 0, which means f dashed of 0 is 0. And so what you'll need to do when you do your initial conditions, back when you solve the differential equation of the f double dash minus kf equals 0, is that you will need to differentiate the f before you put the 0 in. And that will switch your sines to coses and your coses to sines, which will be what causes you to allow you to have solutions that you have. Okay, so you'll then go so when later you sub in your derivatives, you're going to have to differentiate the f before you put the 0 in. All right, that's enough. I'm going to go and have a drink and be back in 3 minutes.